This is Free Range Digital Design Foundation Modeling, Chapter 7. So last chapter we got into actually doing some design. This chapter we're going to talk about some support mechanisms for design, namely timing diagrams. Very important in many aspects of digital design. So timing diagrams, essentially very simple. It's a graphic that shows signal values as a function of time. So the vertical axis is the signal value and the horizontal axis represents time. This is an example timing diagram right here. So these are very useful, typically used to describe digital circuits, describe their operation. It's used to verify digital circuits and typically used to document digital circuits as well. So timing diagrams used for verification, very useful particularly in the outputs of two really common test devices, one being a simulator and one being a logic analyzer. So simulators, they show the expected signal values in your circuit by use of a timing diagram, whereas logic analyzers show the actual values. And the difference being that simulators are using models and not a real circuit to generate output. For logic analyzers, they're used to test an actual implemented circuit. Both of them output timing diagrams. These are example timing diagrams you see out there quite often. This first timing diagram is very simple. It just shows when the signal is high or low. Typically this is the low value, this is the high value. This next timing diagram is a little bit more interesting. We've added these dotted lines on the top and bottom just to make it a little bit more clear. These actually help when you have a lot of signals on a timing diagram. So this third timing diagram here is very similar to the other one, but we're using ones and zeros rather than a high or low. Typically we usually use ones and zeros. They represent numbers, which helps when you have multiple signals, which we'll get into later. So this is another type of timing diagram you see out there where the transition of the signals are slightly slanted. This is more close to being realistic because this represents a discontinuity. Signals do not switch immediately, they switch in a finite amount of time. This notation sort of shows that. You see this quite often, you see all these some of the time. So these are two example timing diagrams related to circuits that we've worked with already. So this of course is an inverter. The output of an inverter is the opposite of the input. So you can see it here when this input, which is X, goes high, the output goes low. When that input goes low, the output goes high, etc., etc. So what I'm doing here is I'm annotating this timing diagram showing the causality of the output by use of these arrows. Now one thing to notice here is the output follows the input immediately. So these are ideal circuits. Typically in a non-ideal circuit there's a delay in that line. We're not going to be showing the delay. So this is an AND gate. You know an AND gate because the output of an AND gate is a 1 when all the inputs are a 1. So what you have in this timing diagram is the X and the Y, they're changing, and eventually for all this time at least one of the inputs is low. But when this input goes high, this input is already high. Let's change that a little bit. This input is already high and we get the output switching from low to high. Once again, this is the annotation, shows causality. I've used these two dots to show that these two signals these two signals both being high cause the output to switch. So this is a truth table that we've been working with before. It was the main example in the previous chapter, and we're going to use this to show a little bit more complicated timing diagram here. So the output is F, it's indicated right here. The three inputs are indicated right here, and what I've done is draw these little dotted lines down the middle of these things to show what these values are. So I'm interested in the values of the input on these dotted lines. You can see this is going to be a 0, 0, and a 1. That's a 0, 0, 1. That corresponds to 0, 0, 1. The index is 1. The output is 0. So you can see the index is a 1. And by all means, this at this point, that output is truly a 0. So we can follow this through. What I'm interested in, we'll look at this time slot here, and what we have here is B2 is a 1, B1 is a 1, and B0 is a 0, so it's a 1 1 0, which is a 1 1 0. The output's a 1, and we do in fact see the output is a 1. So you can step through these things and fill in all the details and ad nauseum at your leisure, or whatever you need to do with this thing. Bundle notation is something we've seen before, we've hinted at. Here's an example of it. So essentially this bundle notation uses a slash in the signal here. You can see the slash in there to indicate that that signal is actually comprised of multiple signals. This little number here indicates how many signals are in that bundle. So this is an example where we start off with something we've seen before, an input with a circuit with 3 single-bit inputs and a single-bit output, and we're changing it to this bundle notation here. So we change the signal name to something that looks clever. B210 kind of sort of relates to this B2, B1, B0. Here's another version here. I got rid of the B210 and just included the B. Once again, it's also a 3-bit signal. These are typical ways to represent multiple signals on a single line. So one thing you never do on these things is make a bundle of one signal. Clutters up your diagram. What we're interested in, the reason we use bundle notation is to simplify and clarify our black box diagrams. And if we can clarify the black box diagram, oftentimes the timing diagrams is much neater, much readable also, which is why we're talking about it now. But it's not always a good idea to bundle signals. So here's an example of a 1-bit adder. It adds 2 bits here, and it outputs a sum and a carryout. No need to worry about this. This is a topic for the next chapter. But the sum and carryout, never mind what they are, but they're distinct signals. So to make it into a bus in this diagram makes no sense. It actually makes it very confusing. I have 2 distinct inputs here. If I group them together in this lower timing diagram, it's for sure going to cause confusion. Don't do it. Bundling signals in the black box diagram oftentimes simplifies the timing diagrams, and this is an example of this. So you've seen this type of notation before, and here's the output. So these are the inputs written as signals. These are bundled signals, and this is how I'm indicating the bundled signals. Notice that the fact that it is a bundle of signals, I'm putting both the high and low on it, and I'm inserting the signal values on the inside. And additionally, I like using this escape character of 0x, which indicates the number that follows it is going to be interpreted as a hexadecimal number. So for example, 0x7 equals 0111, 0x3 equals 0011, etc., etc. I use that everywhere. Oftentimes you see other notation in timing diagrams. Hex is quite popular in timing diagrams. It's represented in a couple different ways. I'm choosing to use the 0x. In this timing diagram, we have these 2 B signals. There's essentially 2 different ways to draw this timing diagram. Inside this timing diagram, I see this 0x1 indicates the interior of this timing diagram is a 001, and we do in fact see a 0, a 0, and a 1, and the output of this is of course a 0, because 001 is this row right here. So you can follow the timing diagram through and run through these things, but the last thing I want to show in this timing diagram is the fact that when all the signals are 0 or all the signals are 1, we can actually represent it differently in the timing diagram. So these are examples of when all the signals are 0. You can see it matches a 0 on the bottom. You see this often in timing diagrams. Certainly you want to use it if you think it makes your timing diagrams clearer. Here's an example of when all the signals in the bundle are a 1. Useful notation. Once again, I do need to annotate this for if I'm going to use bundled signals on this thing, because it's not clear the ordering inside like the B signal. So I actually put a note down here saying B2 is the MSB, B0 is the LSB.